The universe is expanding. The motion of distant galaxies due to this expansion is called the Hubble flow, and it has an interesting, though somewhat trivial, property. The Hubble flow only occurs along the line of sight. That is, if you look at an object in an expanding universe, it will appear to be moving directly away from you. In fact, because of the way the universe expands, at every point in space, every object will look like it is moving directly away from you. And yet, when we look up at the night sky, all the galaxies are not moving away from us. In fact, our nearest neighbour, Andromeda, is moving towards us. This suggests that there is a second type of motion which galaxies can undergo, and that this motion can pull galaxies in any direction. We call this peculiar motion, and, by studying it, we can glimpse something of the processes which result in the formations of vast clusters of galaxies, several billion light-years across. The speed at which galaxies move across the sky is a great measurement of structure growth, because there is no Hubble flow perpendicular to our line of sight. We call this transverse peculiar motion, and all transverse peculiar motion is the result of gravity. However, that doesn't mean it only contains information about gravity. As two masses gravitate towards each other in an expanding universe, their infall due to gravity is slowed because the distance they have to fall keeps increasing. Therefore, peculiar motions also contain information about the expansion of the universe. Unfortunately for us, these motions are very, very small. Even our best satellites, like the European Space Agency's Gaia, are barely able to detect any movement at all. However, they can detect some. To answer my grandmother's question, this year I have been trying to figure out if we can use measurements of how quickly galaxies move across the night sky to measure how fast the universe is expanding. To test this viability, we modelled both what we expect to see on the sky and the errors we expect to have in that measurement. We combined the two to find a quantity called the signal-to-noise ratio, which is 1 over the fractional error in the measurement. A signal-to-noise ratio of 1 is called the detection threshold, and if an experiment achieves this, that experiment has shown that the quantity it is trying to measure is non-zero to about 85% certainty. For context, current measurements of the Hubble constant have signal-to-noise ratios of over 100. How does our measurement stack up? This graph looks scary, but let me explain it. On the vertical axis, we have the signal-to-noise ratio. It is plotted logarithmically, which means each big tick corresponds to an increase in its value by a factor of 10. On the horizontal axis, we have introduced a parameter, r sigma, which we have also plotted logarithmically. R sigma is how many times more precise our current telescopes have to be to achieve the signal-to-noise ratio on the graph. 3 lines have been plotted in these axes. 2 of these correspond to something called the cross-correlation, and 1 to something called the autocorrelation. These are 2 different methods which could be used to approach this measurement, and we have plotted both here because we expect them to be different. There are 2 lines drawn for the cross-correlation method, because the cross-correlation is dependent on the positions of individual galaxies in a way that the autocorrelation isn't. This dependence introduces a new source of error called shot noise, and we plotted the graph both with and without this shot noise to see how significant of an effect it was. Our first conclusion from this plot can be drawn from the similarity of the solid orange and black dotted lines. Shot noise has no real effect. Comparing the black and red dotted lines shows us that the cross-correlation is always a more effective measurement than the autocorrelation, since the red line remains lower than the black line over our entire range of r sigma. Finally, however, we look at what values the signal-to-noise takes. The news, is not good. At present, our best measurement of the Hubble constant has a signal-to-noise ratio of around 0.5. This is better than it could be, but it is not detection. By tracing an imaginary horizontal line corresponding to detection and tracing down to the x-axis, we see that we would have detection if we could double our experimental precision. While that may sound like good news, and it is certainly better news than we expected when beginning this project, we must remember that we need much, much better than detection to compete with modern results. At r sigma equals 100, this method may be able to meaningfully contribute to our understanding, but we are unlikely to achieve this anytime soon. It seems likely, then, that the answer to the question I set out to answer is no. We can't use measurements of how quickly galaxies move across the night sky to measure how fast the universe is expanding.